Let me begin with a word of prayer. Everybody here. Heavenly Father, we thank you for this day. Thank you for this class. Just ask you to just bless our work today. Or you didn't have to, Jesus. Amen. So today, I have good news and I have bad news. The bad news is I haven't graded your test. The good news is I haven't graded your test. So, all right, anyway, so we're talking about the calculus of vector fields. And so, this is often, AKA is vector calculus. So that's what is vector calculus? Vector calculus is the calculus of vector fields. And so, let me just begin with well, what is a vector field? Right, so definition, a vector field on S, right, which is, let's say, some subset of Rn, is an attachment of a vector at each point in S. Now I realize that definition, if you're a math major, is a little bit vague. And that's intentional because I'm trying to cover a lot of things with this. Like, you can talk about vector field along a curve, you can talk about the vector field along a surface, you can talk about a vector field through a volume, you could talk about vector fields through higher dimensional things. But specifically, we often have in mind vector fields in R2. Vector field in R2, something would look something like F is equal to, let's say, P comma Q, typical notation. But of course, you could also write this as, say, P x hat plus Q y hat. And I would say conceptually, maybe the difference, at least between a vector field and, say, vectors that we identify with points is that we envision vector fields being attached at the point of their application. We don't necessarily base them at the origin, right? But this is a vector field in R2. In R3, a typical notation, and I suppose I should fess up and mention I am using slightly non-standard notation. I mean, not everybody would use the bracket notation in this context. Mathematicians will, because it's just this easier notation. And certainly physicists you'll find using this notation. But oftentimes in math books, in usual calculus 3 books, what do you find here? And also in physics, you'll see what? Depending on which physics book you have, but you'll see this I hat, J hat notation, right? So the I, as we talked about at the start of the course, the I, J, and the K, those are in honor of Hamilton and his quaternions. And Hamilton quaternions are built from I, J, K. Not vectors, though. Those are imaginary units that square to -1. And they anti-commute. So that's a different story altogether. But anyway, the reason that the I, J, K notation goes back to Hamilton. So these are vector fields. Let's just let me. So, here's an example. We could have, for instance, F equal to, and so, okay, so here's the thing. Technically speaking, I should write this. F of xy is equal to, like, x over the square root of x squared plus y squared, y over the square root of x squared plus y squared, right? A lot of times, I get tired of writing f of xy, and at times I will omit the of xy here and just write f is equal to the formula I wrote, right? Now this vector field I just wrote here, can you guys tell me what is this vector field? We have another notation for this actually. What is this?
It's a gradient of the sphere.
Gradient of a circle.
That's right.
It's a circle. It's got something to do with the circle, I agree. What direction does it point? What's the length of this vector? At any xy, what's the length of xy? I heard 1. And which way does it point? In the xy direction, right? Search your heart. Realize that this is r hat. It's the unit vector which points radially out from the origin. 2 dimensions. So if I draw it, right, if I pick, say for instance, a unit circle, and I just draw the vectors as they emanate from the unit circle there, you know, it's something like this. Those are all supposed to be length 1 vectors if I draw them, you know. And again, as we talked about before, when you're picturing a vector field, there are options. Sometimes you don't actually draw the vectors as if they're actually their length to scale, right? You're more interested in the picture indicating the directionality of the vector field. Okay, so let me remind you. So this vector field, right? Let's see here. If we were to try to find an integral curve to this vector field, what would that have to solve? What would an integral curve to this vector field be? So we defined this before, but integral curve would be a vector, a curve which lines up with the vector field. And I have to draw more of the vectors, right? Like if I just, for the sake of just not going nuts, let me just draw some here, right? If we go out, it's just like that, right? So if I want the integral curve to this vector field, which goes through the, say, the point, this point right here, what would it be? Integral curve through P. Integral curve, sometimes also called a flow line or a streamline. In that terminology, you have in mind the idea that this vector field is like a velocity field of a liquid or something. So if you could imagine dropping a drop of dye into the liquid and watching how the dye spread out, it would flow along this flow line, streamline. And it would literally be a line here, right? You guys can kind of see it, right? Just like this, right? This would be the streamline. In that case, it's a ray from the origin. So this vector field, the streamlines are just rays that emanate out of the origin. And you can find the streamlines if you're willing, if you're able, by solving differential equations. See, because the equation for the integral curve is that if you feed the parameterization of the curve into the vector, well then we get the velocity, the derivative of the vector. Excuse me, not of the vector, but of the parameterization of the path, right? If I parameterize the integral curve by gamma, then for it to be an integral curve is to say that f of gamma of t is equal to the gamma of t. But what that means, if we let gamma equal to x comma y, see, well, what we're trying to solve there in this context is, well, we're trying to solve dx dt and dy dt equals to certain things, right? And what would those things be? Well, in this case, they'd be x over the square root of x squared plus y squared, and y over the square root of x squared plus y squared, right? And as I described to you guys, whenever we have an autonomous system of differential equations like this, in view of the chain rule and a little bit of sneaky business, we can solve these essentially by dividing the differential equation and solving the resulting equation for x and y. let's just do that for this example. I'm trying to use one example to showcase about a half a dozen different ideas.
And how did you get those differential equations?
That is, so this right here gives me those, both of them. See, because that's the x component, and it has to, on the other hand, be equal to d gamma dt. D gamma dt is, in our notation, dx dt dy dt. See? So I have dx dt is equal to that, dy dt is equal to that, each of those. Now I can eliminate time by dividing the velocities, right? In other words, I can go, well, dy dx is actually equal to dy dt divided by dx dt, you see? And for us, dy dt is y over the square root, x squared plus y squared, divided by x over the square root of x squared plus y squared. Well, whew, that's a relief. Look what goes away. See what goes away? The square root's gone away, and lo and behold, we're back to a problem in calculus 2 that we probably was one of our most favorite problems to be confronted with in all of calculus 2, because when this hits you, you're already good on integration, and this is like a welcome relief from the rest of the course, right? This part of the differential equation that's solved by separation of variables, for me, this was a nice. Students usually get this part of Calc 2 the best, you know? Dy over y equals to dx over x. Integrate those things. Natural log absolute value of y is equal to the natural log of the absolute value of x plus a constant. Exponentiate that thing, that gives you y is equal to plus or minus e to the c times x, which of course we get y is equal to kx. So there you go. The solution to the differential equation, of course, are lines through the origin. All right. But what's the rub? At the origin, the vector field is not defined, right? This vector field is not defined where? Right there, right? That's the one place it's not defined. So the domain for this vector field is R2 minus the origin, right? This is the so-called punctured plane. The punctured plane is the plane with one point removed, usually the origin. This vector field is defined on the punctured plane. Its streamlines are raised from the origin. Can you think of anything else we could do to describe this vector field? It's kind of boring because it's always length 1, right? How about this? The other way we could describe the vector field is that its streamlines are perpendicular to what? I'll ask that question. This vector field, describe this vector field in example 1. Its streamlines are perpendicular to what? To a particular family of curves. What are those curves? I've got one already drawn, right? They're perpendicular to circles, right? So circles with the form what? X squared plus y squared equals to r squared, right? The streamlines are perpendicular to circles. What's the significance? What's the significance of the streamlines? Well, what's the significance of the set of curves which is perpendicular to the streamlines? Can you tell me? Oh, it's not quite that, is it? Oh, man. Well, okay, so it's not direct. I was hoping that the gradient of the streamline of the curve function here would give me the vector field. That's not quite the case, is it? Check it out, though. The gradient of x squared plus y squared is what? It is 2x, 2y, right? So, but this much is true. That's equal to what? The square root, well, it's equal to twice the square root of x squared plus y squared, right? Times what? Times my vector field, right? Times r hat. kind of thing I want to see. So that's the geometry if you think about it. The streamlines are going to be perpendicular. Whatever the streamlines are perpendicular to, that family of curves, the gradient of that family of curves should do what? It should match up the direction of the given vector field. If you trace through the way things are perpendicular here. Right? Because, remember, if we have a level function x squared plus y squared, what its gradient points what? It points perpendicular to the direction of its level curves, as we discussed before, right? So perpendicular to the direction of level curves is parallel to the streamlines in this context. Right? So we have a special definition. So there's two kind of ways you can go specializing geometric comments about vector fields. The one is what I have over here, the equations for the integral curves, which we don't tend to emphasize in Calculus 3 because that's more a problem of differential equations, right? But I do think it's part of the discussion here. It's worth our time to talk about this. But the other thing you could do is say, well, what if I want to have my vector field directly to be the gradient of something else? See, that's another way we could hopefully characterize. Maybe we can write possible to find a little function f such that the given vector field is equal to the gradient of that function f, right? I'm not sure, actually. With this particular example, can I do it? You guys have had this problem in homework already, right? I've asked you this question before. Find the function whose derivative matches the vector field. I didn't call it a vector field, but you have done the algebra, the calculus for this task already. And I can foolishly try to do it for our example right now because I really don't know if this is going to work out. I chose what I did here because it was easy to picture, but can we find f is a tougher question. Why? We got to do what? Gradient of f. We know partial f, partial x, right? Partial f, partial y. And we're given that those are what? X over the square root of x squared plus y squared, and y over the square root of x squared plus y squared, yeah? So we've got to solve what? We've got to solve partial f, partial x equals to x over the square root of x squared plus y squared, and partial f, partial y equals to y over the square root of x squared plus y squared. And you solve those. If you can solve one, you can solve the other, right? They're completely symmetric with respect to x and y. So it's an all or nothing kind of deal here, isn't it? No power series, Sam. If you were going to go down that path, it'd be binomial series for you this time.
Natural log.
Natural log is the way to go here. Natural log of x squared plus y squared is not quite what we want. Think about it though. What happens when you differentiate that? Yeah, you get a 2x upstairs, but you get division by x squared plus y squared. But we can fix that by slapping a 1/2 up here. Right? Oh, but that's problematic because now, rats. Well, maybe it's not what I thought it was. Oh. Thought I had it for a second there. Trig sub? Maybe. Is this a U sub? I think it's a U sub, isn't it? So we're just integrating, partial f, partial x with respect to x and holding y fixed, right? So integral of x I'm just gonna use dx because I don't like it. And I'm holding y fixed, I should write that somewhere. If I let u be that, then I've got integral 1/2 du over the square root of u. Oh, that's integral of du over 2 square root of u. What's the derivative of 2 square root 1 over 2? Hey, that's just square root of u, right? Am I wrong? So here, it's a constant, which is a function of y in this context, right? So square root of x squared plus y squared plus c1 of y. But you can see by the symmetry of the problem that we're not going to have that be in any, this function is only going to really be just a constant. Okay, anyway. This is integration, so it boils down to educated guessing. I think we've educated ourselves enough. We can see that little f is equal to the square root of x squared plus y squared. That will do nicely. Right?
What do you need a 1/2?
Would we? Yes, we would. Thank you. Forgot my hat already. My bad. Thank you, thank you. So if we differentiate that, we calculate the gradient of this function, we get back our vector field. Right? Except where? X squared y squared equal to 0, right? Where all your partial derivatives actually have vertical tangents. At 0, you've got square root of 0, which is, it's kind of like a vertical tangent from every direction. So the origin is out, but that's okay. Because you can see that we have f is equal to the gradient of little f on R2 minus the origin, right? So let me tell you what this all means. This means that the vector field that we're looking at, namely r hat, is what's called a conservative vector field, all right? Definition. F is conservative on U, subset of Rn, okay? If and only if F is equal to the gradient of some little f on U. So a conservative vector field is one for which there exists a so-called potential function, the gradient of that potential function giving you back the vector field. Now, not all vector fields are like this, right? As we've talked about in some homework before. If your vector field isn't nice, then it's not possible to find a potential function because of the fact that partial derivatives commute. So if the components of your vector field don't play nice, then, like for example, if we had, say, g of x comma y is equal to, say, minus y comma x, we're not going to be able to solve and find a potential function for this. All right? You could say, is this equal to the gradient of some little g? Question mark. Well, if it did, you'd on one hand have partial g partial x equals to minus y, and you'd also have partial g partial y equal to x. But what would this say? This would say that partial squared g partial x partial y, I'm really not enjoying writing that, it's minus 1. And this would say partial squared g partial y partial x. Oh man, I should have done it the other way. Yx, xy. Trying to reflect the order of operations here for a moment. That's equal to 1, but we know, and I'm going to go back to the better notation, gxy is equal to gyx, which gives me minus 1 equals to 1, which is unhappy. Or it's happy, because what does it mean? Now let's be optimistic. It's happy. Why is it happy? It's happy because if the question was find the potential function if possible, at this point we have come to the point of impossible. So our job is done. This shows that G is not conservative. G is not conservative. And more than that, because this calculation is completely independent of my choice of y and x, there's no like sneaky restriction of the function, a restriction of the vector field that I could make in terms of its domain to make it conservative. This on you business is not just for decoration. We're going to see over the next weeks that the choice of you matters. The topology of you actually matters. It'll take us a little while to get there. But this is basically what we're after. This is a discovery. Like, I'm not showing you how to solve a problem right now, right? I'm trying to show you some ideas that illustrate the geometry of vector fields to start a discussion. So let me tell you the questions we're going to ask and answer. We're going to ask the question, when is it possible for the vector field to be conservative? We're going to give characterizations of that. There are going to be 4 really separate, independent characterizations of what it means for a vector field to be conservative that we'll look at. We'll then also look at what's called a line integral. A line integral will calculate how much of a vector field lines up along a curve. Or physically speaking, a line integral will calculate the work done by a vector field along a curve. All right? Or you could also call it the circulation. It tells you for a velocity field how much of a liquid actually would be circulating around the curve in that sense. Then we'll look at something called flux. Flux is basically a way to count the number of field lines that pierce a surface. Number of flow lines, if you will, number of streamlines that pierce a surface relative to some convention. And so the flux of a vector field to the surface is an important thing for physics. The laws of, for example, electromagnetism are all written in terms of flux. If you study fluid dynamics, also again, flux is a large part of the story because you can, the flux of the velocity field for a fluid through some surface would describe how much of the liquid is actually flowing through that membrane, let's say. So flux is a very important idea, and we need to talk about how to calculate that. And we'll discover that both the circulation and the flux, the line integral and the surface integral in 3 dimensions, there are beautiful theorems which link these two eventually. These theorems are called the divergence theorem and Stokes theorem. That's usually the culmination of this course, is to prove and discuss the divergence and the divergence theorem and Stokes theorem. Now, before I get to that, though, there's more basic theorems of integral calculus. We'll cover like the fundamental theorem of calculus for line integrals. I think that's the first thing we'll get to is that. And before we get to the deeper things, we'll also get something called Green's theorem, which is an especially 2-dimensional theorem that relates an area integral to the line integral around the boundary of the area. So that's where we're going. We're going to discuss these things. But in these things, there's 3 kind of derivatives that come up. The one you've already seen, the gradient, right? The gradient is one kind of derivative that you see, but there's 2 other derivatives that come up in that larger discussion I'm giving, which is those 2 derivatives are the divergence and the curl of a vector field. So to kick off this part of the course, I just had you guys start calculating those just to get familiar with what they mean. Because you can do that independent of like the deeper understanding of what they mean geometrically. Our goal is to understand geometrically what the divergence and the curl mean, but it takes a couple weeks to really get to it, through it. But nothing's stopping us from doing some homework on how to calculate the curl and the divergence right now, so let's get into it. Here's the definition. These are both, well, you could define the, I suppose you could get 2-dimensional definitions, but I'm going to stick with a 3-dimensional definition, all right? So let F equal to, I'm going to use F1, F2, F3 for the components of it, and G be another vector field, G1, G2, G3, okay? So the divergence of F, which is denoted del dot nabla dot F like this, which if you want to be boring, you could also say div F, the divergence of F, all right? it is equal to partial f1 partial x plus partial f2 partial y plus partial f3 partial z, which of course you could also write succinctly as the sum I equals 1 to 3 of partial f sub I partial x lower I. The divergence of a vector field is a scalar field. It's a function. All right. The divergence of a vector field is a function. And you kind of might guess where this is going, right? I just took the dot product with nabla. What else might I try? How about the cross product with nabla? So the del cross f, which is also called the curl of f, or in some older books, the rotation of f, or rot f. Well, this is equal to the sum. I'll use I, j, k equals 1 to 3 of epsilon I, j, k, partial I, f sub j, all of that times x hat sub k. I can give you the mnemonic for this, which is in terms of the determinant. Our usual thing for the cross product, we put x hat, y hat, z hat in the top row. We put partial x. Actually, if you don't mind, I'm going to write that as partial sub x, partial sub y, partial sub z, because it's just more fun to write it that way. And then f1, f2, f3. Now you have to understand what this means. What does that mean? We're talking about, for x hat, we've got partial y f3 minus partial z f2, comma, partial x, my bad, partial z f1 minus partial x f3, comma, partial x f2 minus partial y f1. That's the curl of a vector. So let's see here, example 3. How can we make example 3 three-dimensional? I mean, how can we make example 2 three-dimensional with you? There's kind of a simple way to make that three-dimensional, right? What if we let f equal to, just slap a 0 on it, right? Minus y, x, 0. All right? Let's take the curl and the divergence of this thing. What's the divergence of f? So we've got partial x of minus y plus partial y of x plus partial z of 0. All of this is 0. The divergence of this vector field is 0. How about its curl? Curl of f. Pick your favorite formula. Let's see here. I like, let me show you yet another way to think about curl. Okay, guys? Watch this. You can think about nabla as like a vector. So it's like this. It's x hat partial x plus y hat partial y plus z hat partial z. That is the nabla. And we're taking the cross product of that with f, which is what? Minus y x hat plus x y hat. And so the only things that are non-trivial here are, and so the differentiation doesn't do anything to x hat and y hat. Why is that? Do x hat and y hat have a point dependence? No, they're just either 1, 0, 0 or 0, 1, 0 everywhere. So the derivative doesn't act on the x hat and the y hat, so kind of just let those ride along. But x hat, Cartesian product of y hat gives you z hat. So on the one hand, you have partial x acting on x, right, times x hat cross y hat. On the other hand, the other non-trivial player in this game is the partial y acting on the x hat term, right? So this one acting on that one gives me, and then minus pulls out, minus partial y acting on y, y hat cross x hat, right? So what's that give you? Well, that gives you 2 z hat. So if you guys have been ignoring me and just working out this thing in the meantime, you should have got 0, 0, 2. Because all of these derivatives are 0 except for the last component, right? All of those derivatives are 0 except for the third component where you get 1 and 1. We get 1 and minus 1, but 1 plus minus 1 is 2. This is not an accident. This is not an accident. We will prove, here's a theorem we'll prove in due time. Theorem, if you have the curl of a gradient of a function, let me say g here, you get 0. The curl of a gradient is 0. So what does that mean? Let's think about this. If a vector field is conservative, it's equal to the gradient of a potential function, right? So if the vector field is the gradient of a potential function, then what's the curl of that vector field? So if g is equal to not little g, then the curl of g is the curl of the gradient, which is equal to 0, right? But that's not the case here, is it? The curl of this vector field, I changed it to f, rats. Well, I can fix that. No, I won't, I'll change this to f. There you go. I gotta stop changing my letters. So the point that I'm trying to make at the moment, how many of these tall chairs do we need in here? This is like we need 2 tall chairs in our room. This is weird. Who brought this thing in here? Anyway, if the vector field is conservative, it must have a curl which is 0. This vector field has a curl which is 2. Therefore, it's not conservative. So what this is doing is it's systematizing that rule we had before that the mixed partials have to be equal in order to integrate, to find the potential. This is making it nice and streamlined. Any questions? So of course we'd like to know what the properties are of the divergence of the curl, right? And they have many properties, like they're linear, there's a product rule, there's all kinds of rules, all right? But I don't want to do those today. I want to just show you some more examples in the time that remains. Let's try another. So we'll probably prove the properties of the curl and divergence like next class. And hopefully next class we'll look at the properties of the curl and divergence, and we'll likely also define the line integral next class. There will be a quiz Tuesday on curl and divergence in the right? So I just want to make sure we're all on the same page. We know how to calculate like the curl and the divergence. They're not hard, but we just have to follow the cross product pattern and all that. So let's see, example 4. I won't try to be preachy with this example, I'll just try to show you the mechanics of something. So let's say f is equal to, I don't know, cosine of xy, yz plus x squared. And then, how about a e to the minus z? Let's calculate the curl and the divergence of this vector field. We'll start with the divergence because it's super easy, right? Divergence isn't bad. We just got to do partial x of cosine of xy plus partial y of yz plus x squared plus partial z of e to the minus z. So what do we get? We get minus y sine of xy plus z minus e to the minus z. And there you go. That's the divergence. The divergence is a function. You shouldn't be getting a vector. You should be getting a single quantity, which is a function of x, y, and z, right? And I see I've failed to move my camera. Daniel's like, if you want me to move the camera, put it where I can actually get to it. Correct? And now for the curl. Do the curl. So, curl of f, and I'll use the mnemonic here. We've got x hat, we've got y hat, we've got z hat. We put partial x here, we put partial y here, we put partial z here. I got my cosine of xy for that component, yz plus x squared for this component, and then e to the minus z for my z component of the vector field being curled. All right, so I'll start out with x hat. So x hat, we've got partial y of e to the minus z minus partial z of yz. Now, when we did the cross product before, we had the luxury of either writing the components from the second row first or the third row first, right? But here, you have to do the second row first, followed by the third row, because we want the partial derivatives to act on the functions. And the opposite way is not the same thing. All right? Do you guys understand this? What I'm saying, what I'm getting at here? Partial x of xy is a function. This is not equal to xy, partial x, for instance. Function, operator. So the best way you could interpret this would be for the function to be the multiplication operator. That's the only context in which these could be equal. And even in that much, they have to only be equal on a very specific subset of all possible functions. Anyway, let me finish this thing. So then we have a minus y hat times partial x e to the minus z minus partial z cosine of xy plus z hat. And there we've got partial x of yz plus x squared minus partial y of cosine of xy. Let's finish this thing here. So we got our curl is, that's 0, that is y, there's minus. So minus y comma, let's see here, 0, 0, minus y comma 0, and my z hat. I got a y. And what else? Oh, plus 2x. And over here, plus x, sine of xy using the chain rule, right? So there you go. Obvious follow-up question, is this vector field conservative? No. Definitely not. Its curl is not 0, right? To make this vector, to make the curl 0, I would have to, I have to have so many things 0, it probably doesn't really leave me much to anything. No. Anyway, that's what we're getting into here, guys. Sorry I don't have your test graded yet, but on the other hand, you're welcome.